Okay, this is on graphs of absolute functions, and here's a absolute value function right here. D of t equals the absolute value of t minus 2 plus 5. So absolute value makes a number positive. So I'm just going to plot some points in here to see what it looks like. Like, for example, substituting -1 in here. -1 minus 2 is -3. Absolute value of -3 is 3, and 3 plus 5 is 8. So I'm just plotting some points. Like, let me do another one here. Let me say I put 4 in here. 4 minus 2 is 2. Absolute value of 2 is 2. It keeps it positive. 2 plus 5 is 7. Now, once you have these points, you can plot them by hand. Like -1, 8 is right here. 0, 7. 1, 6 is right here. And what you find is that you get this V-shaped looking thing. Now, this point is called the vertex point of this shape. You can get the vertex point, the x part of the vertex point, by setting what's in the absolute value equal to 0. If you set t minus 2 equals 0, you'll get t equals 2. So the x part of the vertex point is at 2. And then to get the y part of the vertex point, just substitute that back in. 2 minus 2 is 0. Absolute value of 0 is 0. 0 plus 5 is 5. So that's the vertex point. You know that the v is opening up because the leading coefficient, the number in front of the absolute value right here, is assumed to be a 1 right there, which is positive, which means it opens up. So these are very similar to parabolas, a different shape, but same way of getting vertex points and knowing whether it opens up or down. Okay. So now, solving an absolute value equation, can be a little bit tricky. So let's go ahead and solve this one right here. 7 equals the absolute value of t minus 2 plus 5. What you want to do with these is isolate the absolute value. So the first thing you need to do is subtract 5 from both sides. If you do that, you get 2 equals the absolute value of t minus 2. From an absolute value equation, you get two linear equations. The reason for that is because absolute value makes positive numbers positive, and it also makes negative numbers positive. So from this one equation, we get 2 equals t minus 2. In other words, just remove the absolute value, but you get a second equation, -2 equals t minus 2. And that's the trick to solving absolute value equations. Isolate the absolute value and then write two equations from that. One where you just drop the absolute value, and the other one where you change the sign of the other side of the equation. Change the 2 to a -2. Then solve both of these. Adding -2, you get 4. And then here on the second equation, you have to add 2, and you'll get 0. Now, with absolute value equations, there's a chance that both of these will work. Here's my two possible solutions, 0 and 4. Maybe both will work, maybe none will work, or maybe only one of these two solutions will work. Well, let's check them. So you have to check these back in. You really have to check these. Put the 4 in there. 4 minus 2 is 2. Absolute value of 2 is 2. And 2 plus 5 is 7. So the 4 works. Check the 0. 0 minus 2 is -2. Absolute value of -2 is 2. 2 plus 5 is 7. So it works. Yep. Now, this is saying about how you get your two equations. And you know, there could be a chance that you get no solution. Like, for example, if this would have been absolute value of this, like when I isolated it, and it was a negative number here, well, then it would have had no solutions. You could have gone through and solved it and got possible solutions, but they wouldn't work. Because if this would have been -2 equals the absolute value of t minus 2, then absolute value makes a number positive, and a positive can't equal a negative, so it would have had no solution. Okay, on this one, we're supposed to give the location of the vertex point. Well, to get the x part of the vertex point, set what's inside the absolute value equal to 0. If you set x plus 4 equals 0, you get -4. So the x part of the vertex point is -4. Plug the -4 back in, you'll get 0 here. -3 times 0 is 0. 0 minus 2 is -2. So that's the y part of the vertex point. This would be a absolute value function that opens downwards because this is negative right here. And it would be a little bit thinner because the bigger this number is right here, the thinner it is. So it has a vertex point at -4, -2, and opens downward. If it says what's the x-intercept for this problem, I know it has no x-intercept because it's already below the x-axis and it's never going to come around back up. It's just this upside down V shape right there. Alright, here's one. This one says graph this function and give the location of the vertex point and state whether it's a max or a min. So to get the x part of the vertex point, again, set what's inside this absolute value equal to 0. So I would need to set the negative 3x plus 4 equals 0. So I would subtract 4 and then divide through by negative 3. So I'd get negative 3x equals negative 4, then divide through by the negative 3, and I get x equals 4/3. So that's the x part of the vertex point. And then really the y part of the vertex point is the constant out here as long as there's no extra x. Or you can substitute it back in. If you substitute 4/3 back in here, I know that's going to make that 0 because that's what we said equal to 0. So that's going to be 0. 5 times 0 is 0, and 0 minus 7 is minus 7. So the vertex point is definitely 4/3 negative 7. Does it open up or open down? Well, looking at the leading coefficient, it's positive, so it opens up. And it would be a rather thin v because the number here is bigger than 1. That's not a big deal that it's thin, but it does open up, and the vertex point is at 4/3 negative 7. So 4/3, over here 4/3, which is 1 1/3, and down negative 7 right here, and then it opens up. And this function is going to have 2 x-intercepts to it. And I tell you what, let's go ahead and work out how you would get those x-intercepts now. To find the x-intercepts of this, we have to set y equal to 0. So the f of x is playing the role of y. So we say 0 equals this stuff. So 0 equals 5 times the absolute value of negative 3x plus 4 minus 7. Now, to solve this algebraically, you isolate the absolute value. So add 7 to both sides. Then the next step is divide through by 5. 7 divided by 5 is 1.4. Now from the absolute value, you get 2 equations. One is 1.4 equals negative 3x plus 4 by just dropping the absolute value sign. And the other one is change the sign of the number on the left. So negative 1.4 equals negative 3x plus 4. Now solve both of these equations. Subtract 4 from both sides and I get negative 2.6x equals negative 3x. Then divide both sides by negative 3 and I get x equals 0.866. Over here, same thing. Subtract the 4 and I get negative 5.4 equals negative 3x. Divide both sides by the negative 3 and I get x equals 1.8. Now, we don't know if these are the 2 x-intercepts. These are the 2 possible x-intercepts, so you need to check these. If I substitute the 0.866 in for x, you could do this on a calculator. Remember, absolute value makes this positive, and it will work. And if you check 1.8 on this side, in the same equation, check with 1.8, and check and see if this equals 0. And if you check that, it does. So it works. Now another option is to do this on the AnyGraph sheet. So the AnyGraph sheet is the Excel sheet that looks like this, and it gives you directions here how to type equations in. Like here's an example. So you type in the equation right here in cell B10, and I typed it in right here. You can pause it and see it. It says equals 5 times, that's asterisk, which is shift 8. ABS means absolute value, and what are we taking the absolute value of? Parentheses. 3 times, and you can actually type in the letter x for the letter x, then what? Plus 4 minus 7. So you just type that in. Once you have that typed in, then just hit enter and it will graph it. Now I got it set to graph from negative 5 to 5. If you don't see any x-intercepts, maybe it doesn't have any, or maybe you might have to look over a larger area. But intercepts want it somewhere, they're both between 0 and 2. So I can narrow in on it and look at this graph from 0 to 2. If I do that, now I can see that one x-intercept is between 0.5 and 1. So if I look at that, 0.5 and 1, I can see that one of the x-intercepts is between 0.8 and 1. So just narrowing in on it, 0.8 to 1. And now you can even hold the mouse cursor there to get a good idea, so it's about 0.86. The other x-intercept was a little bit farther out. Here's the other x-intercept. It's between 1.5 and 2. So if I look from 1.5 to 2, then I know it's somewhere around here. Holding the mouse cursor there, it'll pop up and see about 1.79. So what I do is I graph a little bit before that spot, maybe 1.7 to a little bit bigger than that, maybe 1.9. If I do, I can see the other x-intercept is here at 1.8, and that confirms what I got right here. But both options of finding x-intercepts are fine. So I'll stop there and I'll do another video.